Good day and welcome to One-on-One Maths Private Tutors. Today we are going to look at O-Level and IGCSE Physics. The topic is specific heat capacity and latent heat. The internal energy of a body is the sum of the potential and kinetic energies of its particles. Increasing the temperature of the body increases the average kinetic energy of the particles. So we can say temperature is directly related to kinetic energy of particles in a substance. So if you heat water in an electric jug, for example, the water particles will start to move faster. And if you take water into the refrigerator, the particles will start to move slower. The specific heat capacity, C, of a material is the energy required to raise the temperature of 1 kg of that material by 1 degree Celsius. For example, the specific heat capacity of water is 4,200 joules per kg degrees Celsius. So what that means is 1 kg of water requires 4,200 joules of thermal energy to raise it by 1 degree Celsius. Let's say from 14 degrees Celsius to 15 degrees Celsius. So specific heat capacity is the amount of energy required to raise 1 kg of that substance by 1 degree Celsius. In other words, this means that it takes 4,200 joules of energy to raise the temperature of 1 kg of water by 1 degree Celsius. Which brings us to the equation, which we have to recall. Change in energy is equal to mass times specific heat capacity times change in temperature. Energy transferred is equal to mass times specific heat capacity times the temperature change. So from the definition of specific heat capacity, if we divide both sides by m, delta theta and m will cancel there. This side, m delta theta, we will say C is equal to delta E, which is change in energy, over mass times change in temperature. So we must be able to recall and use this equation. Delta E, or E, is equal to mc delta theta, where m is the mass, C is the specific heat capacity, and delta theta is the change in temperature. The units of specific heat capacity, since this is energy, joules, m is mass, kgs, delta theta is degrees Celsius, change in temperature. So the units are joules per kg. Let's look at how we use this equation. Calculating energy. Water has a specific heat capacity of 4,200 joules per kg degrees Celsius. How much heat energy must be supplied to raise the temperature of 1.5 kg of water by 10 degrees? From our equation, E is equal to mass times specific heat capacity times change in temperature, or E is equal to mc delta theta. Question requires us to calculate heat energy, so we want the energy. The mass is 1.5 times specific heat capacity is 4,200 times the change in temperature is 10 degrees Celsius, which is 63,000 joules, which we can abbreviate as 63 kilojoules. So for an exam tip, we must practice rearranging all of the equations by changing subject of the formula. This will help you to reduce the time it takes in the exam. Let's apply that in this question. Here we are calculating specific heat capacity. 150 joules of heat energy are required to raise the temperature of a 100-gram block of metal by 5 degrees. What is the specific heat capacity of the metal? So energy is 150 joules, mass is 100 grams, which we have to convert to kilograms, which is 100 over 1,000, which will give us 0.1 kg. Remember, we have to use standard units. Change in temperature, which is our delta theta, is 5 degrees Celsius. To calculate the specific heat capacity, we use our equation E is equal to mc delta theta. We want C, so we divide both sides by m delta theta, m delta theta, m cancels there, delta theta cancels there. Now we have C is equal to E over m delta theta, which is 150 over m is 0.1 kgs, delta theta is 5. Now we can calculate this, which is 300. Remember the units, joules over mass, kgs, temperature, degrees Celsius. So joules per kg degrees Celsius. So our answer is 300 joules per kg degrees Celsius. So for an exam tip, you must know how to extract information from the question. Read the question carefully and highlight key information such as standard units. Where you are given grams, you have to convert to kgs. Where you are given, say, kilojoules, you have to convert to joules. Know your standard units and select the correct equations to use. Now we go on to the experiment to measure specific heat capacity of a liquid. So this is the setup we have. We have our liquid, let's say water, placed in an insulated container. We do not want to lose heat to the environment. We want all the heat that is supplied by the electrical heater to be used to raise the temperature of the water only. That is why we insulate, and we have the thermometer to measure the change in temperature. So you measure out 0.5 kg of water and pour into a beaker insulated with cotton wool. Place a thermometer in the water and cover it. Place an electrical heater of power 50 watts in the water. Take the initial temperature of the water using the thermometer. Switch on the electrical heater and at the same time start a stopwatch. Stir the water with the thermometer until the temperature has increased by 10 degrees Celsius. Stop the stopwatch and take the reading of the time taken for the water temperature to rise by 10 degrees Celsius. If it takes 7 minutes for the temperature of the water to rise by 10 degrees Celsius, use the information given in the experiment procedure to calculate the specific heat capacity of the water. Which two equations are required? We want to calculate the energy supplied, but we have the power and the time. Our power is 50 watts, and the time taken, we have been given it 7 minutes, which is 7 times 60 seconds, which is 420 seconds. Remember, the standard unit of time is the seconds. So we know power is energy over time. So we'll rearrange this equation to get energy is equal to power times time, which is our power is 50 times 420 seconds, which will give us 21,000 joules. Now we know mass of the water is 0.5 kgs and the change in temperature is 10 degrees Celsius. So from E is equal to mc delta theta, we can rearrange the equation to C is equal to E over m delta theta, which is 21,000 for our energy, over mass, which is 0,5, times delta theta, which is 10 degrees Celsius. So from our calculator, we can say 21,000 over 0,5 times 10, which will give us 4,200 joules per kg degrees Celsius, which is the specific heat capacity of water. So that is how we carry out the experiment. Now let's move on to melting, boiling, and evaporation. When a solid is heated, it may melt and change its state from solid to liquid. If ice is heated, it becomes water. The opposite process, freezing, occurs when a liquid solidifies by cooling. A pure substance melts at a definite temperature, called the melting temperature or the melting point. It solidifies at the same temperature. Sometimes this is called the freezing temperature or the freezing point. At standard atmospheric pressure, the melting temperature of water is 0 degrees Celsius. Let's look at this experiment on the cooling curve of stearic acid. Safety precautions is to use eye protection and to take care when handling hot water and apparatus. Procedure: half-fill a test tube with stearic acid and place it in a beaker of water. Heat the water until all the stearic acid has melted and its temperature reaches about 8 degrees Celsius. Remove the test tube and arrange it as B, which is this one, with a thermometer in the liquid stearic acid. Record the temperature every minute until it has fallen to 60 degrees Celsius. Plot a graph of temperature against time, which is a cooling curve, and identify the freezing temperature of stearic acid. The cooling curve for a pure substance, which is a plot of temperature against time, is shown in the diagram below. Why is the cooling curve flat in the region A, B? What is happening to the liquid over the region AB in this diagram? Is the rate of cooling faster or slower at high temperatures? Solidifying, melting, and boiling. The previous experiment shows that the temperature of liquid stearic acid falls until it starts to solidify at 69 degrees Celsius and remains constant until it has all solidified, which is shown by the straight line AB. So when we are changing state from liquid to solid, which is here, so from A to B, it's a mixture of liquid and solid. When all the liquid has turned to solid, the temperature starts falling again. But when the mixture is liquid and solid, the temperature remains the same. The cooling curve is for a pure substance. The flat part AB occurs at the melting temperature when the substance is solidifying. During solidification, a substance transfers thermal energy to its surroundings, but its temperature does not fall. Conversely, when a solid is melting, the energy supplied does not cause a temperature rise. Energy is transferred, but the substance does not get hotter. For example, the temperature of a well-stirred ice-water mixture remains at 0 degrees Celsius until all the ice is melted. Similarly, when energy is supplied to a boiling liquid, the temperature of the liquid does not change. The temperature of pure water boiling at standard atmospheric pressure is 100 degrees Celsius. So we can see this is what we call a heating curve. So for a solid pure substance, if we heat it, the temperature will increase until it starts melting. So from this region to that region, we have a solid. Then when it starts melting at that point to that point, we have a mixture of solid and liquid. Energy is supplied, but the temperature does not rise. All the energy is used to change state from solid to liquid. When all the solid has become liquid, then we have temperature rising. So in this region, we now have a liquid. Now, when the temperature has risen high enough to the boiling point, the liquid starts turning into gas. So from this point to that point, we have a mixture of liquid and gas. When all the liquid has turned into gas, then we can now have a temperature rise. So now in this region, we have gas. This is a heating curve. Now for a cooling curve, we start with a gas that is being cooled to the boiling point or condensation point. At the condensation point, which is the same temperature as the boiling point of that particular pure substance, the temperature does not decrease. So in this region, we have a gas, and in this region, we have a mixture of gas and liquid. When all the gases turned to liquid and we continue cooling, the temperature falls again. So in this region, we have a liquid. Now, at a particular temperature known as the freezing point, which is the same as the melting point for that particular pure substance, the temperature remains constant and solid. When all the liquid has turned to solid at this particular time, the temperature starts falling. And in this region now we have a solid. So the heating curve is the opposite of the cooling curve. But these particular points of temperature are maintained. The boiling point being equal to the condensation point, the melting point being equal to the freezing point for a particular pure substance. Latent heat of fusion. Energy that is transferred to a solid during melting or given out by a liquid during solidification is called latent heat of fusion. Latent means hidden and fusion means melting. Latent heat does not cause temperature change. It seems to disappear. So at this point of melting or freezing, that's where we experience latent heat of fusion. Latent heat of vaporization. Latent heat is also needed to change a liquid into vapor. The reading of a thermometer placed in water that is boiling remains constant at 100 degrees Celsius, even though energy, called latent heat of vaporization, is still being transferred to the water from the heating source. When steam condenses to form water, latent heat is given out. So at this point, on a heating curve, the energy taken in to change state is called latent heat of vaporization. And the energy given out when cooling a gas into a liquid is also called latent heat of vaporization. So to define latent heat, we say latent heat is the thermal energy absorbed or released by a substance to change its physical state, such as solid, liquid, or gas without changing its temperature. And the latent heat of fusion is the amount of thermal energy required to change a substance from solid to liquid or from liquid to solid without any change in temperature. It occurs at a constant melting or freezing point, where the energy supplied is used to break intermolecular bonds rather than change the kinetic energy or increase temperature. And the latent heat of vaporization is the amount of thermal energy required to change a substance from a liquid state to a gaseous state or from a gaseous state to a liquid state without any change in temperature. The energy supplied is needed to break down intermolecular forces rather than increase temperature, and this occurs at a constant boiling or condensation point. Let's look at change of state and the kinetic particle model, melting and solidification. The kinetic particle model explains that energy absorbed in melting is the energy that enables the particles of a solid to overcome the intermolecular forces that hold them in place. And when it exceeds a certain value, they break free. Their vibratory motion about fixed positions changes to the slightly greater range of movement they have as liquid particles, and the solid melts. In the reverse process of solidification, in which the liquid returns to being a solid, where the range of movement of particles is less, potential energy is transferred from the particles to thermal energy in the surroundings. The energy input in melting is used to increase the potential energy of the particles, but not their average kinetic energy, as happens when the energy input causes a temperature rise. Vaporization and condensation using the kinetic particle model. If liquid particles are to overcome the forces holding them together and gain freedom to move around independently as gas particles, they need a large amount of energy. This energy increases the potential energy of the particles, but not their kinetic energy. Energy is also required to push back the surrounding atmosphere in the large expansion that occurs when a liquid vaporizes. In the reverse process of condensation, in which a vapor turns to the liquid state, where the particles are closer together, potential energy is transferred from the particles to thermal energy in the surroundings. Boiling and evaporation. At standard atmospheric pressure, the boiling temperature of water is 100 degrees Celsius. For a pure liquid, boiling occurs at a definite temperature, called its boiling temperature or boiling point, and is accompanied by bubbles that form within the liquid, containing the gaseous vapor from the particular substance. Energy is needed in both evaporation and boiling, and is stored in the vapor, from which it is released when the vapor is cooled or compressed and changes to liquid again. Evaporation. A few energetic particles close to the surface of a liquid may escape and become gas particles. This process of evaporation occurs at all temperatures, unlike boiling, which occurs at a particular temperature called the boiling point. Conditions affecting evaporation. Evaporation happens more rapidly when the temperature is higher. Since then, more particles in the liquid are moving fast enough to escape from the surface. Evaporation happens more rapidly when the surface area of the liquid is large, so giving more particles a chance to escape because more are near the surface. Evaporation happens more rapidly also when there is a wind or a draft blowing over the surface, carrying vapor particles away from the surface, thus stopping them from returning to the liquid and making it easier for more liquid particles to break free. Evaporation into a vacuum occurs much more rapidly than into a region where there are other gas particles. Cooling by evaporation. In evaporation, energy is transferred to the liquid from the surroundings, as may be shown by the following demonstration done in a fume cupboard. So the experiment goes like this. Dichloromethane is a volatile liquid. It has a low boiling temperature and evaporates readily at room temperature, especially when air is blown through it. So let's look at this diagram. We have a can, we have water below the can, a block of wood, and in the can we have dichloromethane. Air is being blown into the dichloromethane. Energy is transferred first from the liquid itself and then from the water below the can. The water soon freezes, causing the block and the can to stick together. So energy is being taken away from the dichloromethane, which in turn takes energy from the water, and then the water freezes, making the block of wood and the can to stick together. Explanation. Evaporation occurs when faster moving particles escape from the surface of the liquid. The average speed and therefore the average kinetic energy of the particles left behind decreases. That is, the temperature of the liquid falls. So, evaporation here of the dichloromethane causes the temperature of the remaining dichloromethane liquid to drop. Cooling by contact. When evaporation occurs from a liquid and the average kinetic energy of the remaining particles decreases, the liquid cools. Thermal energy flows from a hotter object to a colder object by conduction. If an object is in contact with the liquid during evaporation, thermal energy will flow from the object to the liquid. The object will cool until its temperature equals that of the liquid. Uses. Water evaporates from the skin when we sweat. This is the body's way of losing unwanted heat and keeping a constant temperature. After vigorous exercise, there is a risk of the body being overcooled, especially in a draft. It is then less able to resist infection. Ether acts as a local anesthetic by chilling as well as cleaning your arm when you are having an injection. Refrigerators, freezers, and air conditioning systems use cooling by evaporation on a large scale. Volatile liquids are used in perfumes. Now let's look at typical examination questions. A hot liquid is allowed to cool. The graph shows the cooling curve. In which part of the curve is latent heat released? Latent heat is released in this flat region, this horizontal region, which is QR. Our answer is B. What is latent heat of vaporization? The energy required to make molecules expand. The energy required to make molecules expand and move apart. The energy required to make molecules move apart. energy required to make molecules move faster. It is the energy required to make molecules move apart. A hot liquid is poured into a beaker. The graph shows how the temperature of the liquid changes as it cools towards room temperature. What is occurring at the region X? So we have a liquid and a solid. So we should have solidification. But a liquid can also evaporate, so evaporation can occur. So D is the answer. Thermal energy of 1,200 joules is supplied to a 2 kg mass of copper. The specific heat capacity of copper is 400 joules per kg. What is the rise in temperature? E is equal to mc delta theta. So what we want is the rise in temperature. So we want delta theta. Delta theta is equal to E over mc, which is 12,000 over 2 times 400, which we can punch into our calculator as 12,000 over 2 times 400, which will give us 15 degrees Celsius. So our answer is A. Different amounts of energy are supplied to copper blocks of different masses. Which block experiences the greatest temperature change? So from this equation, delta theta is equal to E over mc. Since C is a constant, because we are using the same substance, which is copper, we can say delta theta is proportional to E over m. So we'll test the E over m and see which one is the greatest. For A, we will have 200 over 0.1, which will give us 2,000. For B, we'll have 200 over 0.2, which will give us 1,000. For C, we will have 600 over 0.4, which will give us 1,500. For D, we have 400 over 0.8, which will give us 500. So A will give us the greatest delta theta, because it's giving us the greatest magnitude of E over m. Now let's look at this question from June 2023, O-Level Cambridge. An electric heater is used to heat a sample of metal, as shown in Fig 5.2. There is no thermal energy transferred from the metal to the surroundings during the heating. So we will assume it is insulated. The metal has a mass of 200 grams. So our M is 200 grams, which is 200 over 1000, which is 0.2 kgs. The heater is switched on for 2 minutes and then switched off. The maximum temperature reached by the metal is 40 degrees. So initially it is at 15 degrees. So delta theta, which is our change in temperature, is the final temperature minus initial temperature 15, which will give us 25 degrees Celsius. The power of the heater is 20 watts. Power is equal to 20 watts. So the power and the time will enable us to calculate the energy supplied. So our time, 2 minutes, is 2 times 60, which is 120 seconds. Calculate the specific heat capacity. So we want C. So we know energy is equal to power times time, which is 20 times 120, which will give us 2,400 joules. Now we have to take note here. The specific heat capacity is given in joules per gram degree Celsius. This is not kgs. So when we are using mass, we must use it in grams. So now we use this mass of 200 grams, temperature in degrees Celsius, and the energy 2400. So we will say C is equal to E over m delta theta, which is 2400 over our mass 200 times change in temperature 25, which is 0.48 joules per gram degree Celsius. So that is our answer. With that, we come to the end of the section. Thank you.